Welcome to The Explainer, where we break down big ideas. And today, we're diving into something that honestly sounds like it's straight out of science fiction, but it's not. It is very, very real.
So, let me ask you something. What if you could send a message? A message that was truly 100% impossible to spy on. I mean, in a world where it feels like nothing is safe and quantum computers are on the horizon, threatening to crack every code we have, what would a truly unhackable message even look like?
Well, a team of physicists think they have the answer. And that answer is, well, it's super. Seriously. It's a project that could completely change the game for secure communication. Maybe forever.
All right, a super mystery. We're going to meet the theorist behind this groundbreaking idea. So, what is this super thing, and how in the world does it work? To get to the bottom of it, we've got to meet the person who helped dream it all up.
And that brings us to Dr. Doris Rader. She's a theoretical physicist over at TU Dortmund University in Germany. Now, when you picture a physicist, you might be thinking of someone in a lab coat with lasers and test tubes, right? Well, that's not her. She's a theorist, which means her lab, it's the world of ideas.
The Theorist Lab, where the tools are computers, equations, and pure thought. Okay, so what does a Theorist Lab actually look like? Let me tell you, it's probably not what you have in your head.
Okay, so you have two worlds of physics, right? On one side, you've got your experimental physicists. They're the ones with the lasers, the microscopes, the actual physical samples. But then you have theoretical physicists like Dr. Ryder. Their toolkit? It's supercomputers, it's pen and paper, and it's the power of equations. They're building models of the universe with math and code.
And she says she kind of fell into it. She told us, I felt quite comfortable with equations. It was more our fault when experiments were broken. Basically, after a few too many mishaps in the student lab, she realized, you know what, maybe I'm better with the math. The equations, unlike the equipment, always did what they were supposed to.
Next up, the unbreakable message, the search for truly secure communication. And really, it's that love for equations that put her in the perfect spot to take on one of the biggest challenges out there, how to create a genuinely unbreakable message.
So here's the crazy part. This incredible security, it's not based on some complex new code. No, it's built on a fundamental, unbendable rule of physics. It's called the no-cloning theorem, and it's pretty simple, really. You cannot perfectly copy an unknown quantum state. Why? Because the very act of trying to look at it, to measure it, actually changes it. It's like trying to measure the temperature of a single drop of water with a hot thermometer. You just changed what you were trying to measure.
And this is how it all works. You send your secret key, one particle of light, one photon, at a time. Now let's say a spy tries to intercept that photon to copy the key. Well, because of that no-cloning theorem, the moment they measure it, they change it. It's like leaving behind a footprint. The people on the other end will get a messed up photon and know instantly that someone was listening in. Game over for the spy. All right, now we're climbing quantum ladders to unpack the super solution. But here's the catch for all of this to work. You need a perfect, totally reliable source of those single photons. You have to be able to send them out one by one. And that is a huge technical challenge. It's the whole reason the super solution was even invented.
Dr. Ryder has this amazing analogy to explain it. Imagine you want to make a big splash in a pool. That splash, that's your single photon. But to make the splash, you first have to get all the way up to the top of a tall diving board.
Okay, sounds simple enough. But now for the ladder problem. Your goal is to get to the top of that high dive. The problem, you've only got two ladders, and both of them are too short to reach the top. This is exactly the kind of problem physicists face in these quantum systems. So what do? Well, the super solution is it's so clever. You don't just use one ladder, you use both of them, and you jump from one short ladder to the next, using that motion to kind of swing up to the top. It's a really ingenious workaround. And that swing up move, that's exactly where the name comes from. Yep, SUPER is an acronym. It stands for Swing Up of Population of a Quantum Emitter. It sounds complicated, but it just means you're using this clever trick to excite an atom just enough so it spits out that one perfect photon you need.
From theory to reality, the joy of seeing an idea come to life. So this is a really cool idea on paper, right? But how does something like this jump from being just a theory, a thought experiment, into a real thing that scientists can actually build and test in a lab? Well, for a theorist like Dr. Ryder, this is the absolute best part. She said, you propose something which you think is just your mind, and then it works. It's the best thing. Her team published the paper with the idea, and almost immediately, other scientists around the world ran to their labs, they tried it out, and it worked, just like the math said it would. Imagine that feeling.
And she has this really great way of describing the global physics community. She says it's a lot like folk dancing. It doesn't matter where you are in the world, you can walk into a room, and because you share this passion, this language of physics, you can just connect. You can dance together, so to speak. And all this really leaves us with one final, pretty big question. As these amazing quantum technologies stop being just theory and start becoming reality, we have to ask ourselves, now that we can make a secret truly unbreakable, what will be the first secret we decide to protect?